Hello everyone. Right, back to the display. This is part 2 of the Project X, and in Project X obviously we need to have some user input, and the user input is one of these. It's an encoder. What it is, it's like you use it, you turn this knob, use it like you do a volume control, except this is digital. It uses on this side we've got a common pin and two outputs. This forms a quadratic encoder signal, and we use that to determine how far we turn this knob and in which direction we turn the knob. On the other side is a couple more pins, and this is a switch. If we push the switch in, we can push it in like this. This actually activates this switch, so the knob has two functions, a rotation and a push. So that's what we're going to use, is one of those. And what I've done is I've actually mounted one of those encoders with a few resistors and capacitors on there, and I'll explain them. But basically what I have is this little stand here, and then I can rotate this dial here, this knob which I made, and if we look we can see that the numbers change. I will just turn the light off because I've got my up here my LED light which is lighting everything, and I tried to explain before but I just couldn't remember the right word. The LEDs are powered by a pulse width modulation, so we've got pulse if I can get it around my tongue, pulse width modulation. And so what happens is the LEDs flash at that high frequency that's used. We can't see it, but the camera can pick it up, and that's why we can see when some of these are not lit. But our position, I've forgotten that word now. Right, okay. Our persistence in vision makes these look the same. So I'll just turn the light off just to show you again. So there we go. So now it looks more stable. There is a slight flicker, and there's a reason for that, because there's times when this is not actually lit and running, because I want the microcontroller to actually do some other work besides keeping this lit. So while it's doing the other work, these are not lit, and that's where you can see that slight flicker there. But it's not. You can see it on the camera, and even if I try to shadow it, but you can't see it in real life because our eyes still see it as a steady glow. I'm just going to turn the light on again so it makes things look a lot better. Yeah, so there we are. So you can see that. I should have left it off. Yeah, so we're using a user input. You can still see this. So let me just get it all in shot. So if I turn this, you can see that we can change the value with the encoder. We're going to need one of these as well. So what I'm going to do is I'm going to show you the code for getting a value from an encoder. We also have a button. If I press the button, you can see the red LED lights up. So it's a bit bright, but that's just for my diagnostics. But is this LED? It was just telling me which is it. Oh, I haven't wired them up, but I used to have it so it lit. It's a red, green, blue LED, and I had it lighting red for the button, which I've still got activated, and it was green for one direction and blue for the other direction, but I've removed the code that does that. So anyways, for this I will show you the circuit, but basically it's coming, the encoder is coming in on these 3 wires. So we've got our A and B on these 2, and we've got our switch on this one here. So I'm just going to pause it and set up it to look at the circuit diagram. Okay, so here's the circuit diagram. We should all recognise this from part 1. Oh, that bit. That's our pins that are driving our 7-segment LEDs. This we can ignore. This was just my tricolour LED that I just showed. I was just using this for diagnostics, because I'm currently using a Nano Tiny, and a Nano Tiny does not have USB. There's no UART to USB on a T88, or on the board, on the Nano board. The Nano does, the T88 doesn't have UART. It has SPI, and that's what we do. All this, it has more pins than the normal Nano, but it doesn't have the internal hardware that the normal Nano has. Anyways, I digress, because so we can ignore this. This is just my diagnostic. What we're looking at is the encoder, the rotary encoder. On here you can see that let's just zoom in. On here you can see that we have 3 switches. We have a switch here, a switch here, and a switch here. This is just a push button, which I showed, and this is the rotary encoder giving us our A and B signal. This is a common, and from that A and B signal we can get a quadratic encoder signal, basically. The way that works is, actually I'll tell you in a moment, but what I want to tell you about is the circuit at the moment, and why I've got capacitors and resistors here, and I've got these 3 resistors here. Now these 3 resistors we don't always really need to use. What I'm applying here is I am creating a high signal on all these pins, on all these wires. Let's just use that there. So on this line I am just holding this line high with this resistor, and I'm holding this line high with this resistor, and I'm holding this line high with this resistor. These resistors usually on most microcontrollers, you can use the internal resistors. They have a setting on the pins where you can activate pull-up resistors on the pins, and you can do, let me just get rid of this. You can use, instead of using these 3 resistors to VCC, you can actually use the internal resistors of the microcontroller, and you can set the pins to have an internal pull-up resistor which holds the pins high. Then what happens is, when the switch is close to ground, it grounds out this line and it goes low. But the thing is with switches, they're a mechanical thing, and when you actually switch this switch to connect to this other bit, they tend to bounce, and what happens is, we don't notice, but the microcontroller is going that fast. It noticed that there's a slight little bounce, like a spring, that it clicks this across, because these are like spring-loaded switches, and when they hit the contact they tend to bounce a little bit, which sends more than one signal down the line, and we only want one signal. So what we do is we add an RC circuit a resistor capacitor circuit. And what a resistor capacitor circuit does, it delays the signal slightly while this capacitor drains. And once the capacitor drains, it then pulls the line low, by which time the switch that was closing has stopped bouncing, and so we only get the one signal. So what happens is that these resistors, whether they're external like I've drawn them here or internal in the microcontroller, is when these switches are open, they actually charge up these capacitors. So these capacitors get charged up, and then when we close the switch, this circuit is then pulled to ground via this resistor. But because there's a resistor here limiting the current flow to ground, it slows down the discharging of the capacitor. The capacitor doesn't discharge instantly. It discharges fairly slowly. Microcontroller, in the microcontroller world, to us it's instant, but in the microcontroller world it's slow. So it slowly discharges, and the idea is to have a resistor and capacitor pair that sort of discharges the capacitor just slow enough for the switch to stop bouncing. So by the time this resistor has discharged this capacitor, we have a permanent contact on here, and it's not bouncing anymore, which then pulls the signal low, and it's just one instance of it being pulled low. So I always put this in a circuit because like I'm using a nano tiny here, which is the memory it has is only 8K, whereas people get lazy and if they've got an Arduino Nano or something bigger like an ESP32 or the other bigger microcontrollers you can get now, they have lots of memory and they'll just write code to put in a delay. But the thing is, if you put delays in your code, then you've got to wait for those delays to occur. Although they're fast delays, I find it is much better to use a physical depounce, because it also frees up the memory you have in there. You're not filling the microcontroller with lots of code that takes up memory, which you might need for doing other work. So anyway, that's our circuit for our input of our encoder, which we just have the three inputs. We have the A and B input, which is this one here, A and B, and then we have the switch input, which is the button input there. So that goes into there, and you'll notice I haven't written them there. Right, what we need to look at, I'll explain this in the code. I'll get set up with the code now, and then I'll explain how we do the quadratic encoding to determine a value. So I'll just pause it again. Okay, I've done a little drawing, a little sketch here. I've actually opened up one of the encoder switches to sort of show you how they actually work inside. As I say, I've put some black lines here to this little wiper. Oh yeah, wiper, that's the word, wiper. Yeah, so we've got we've actually got two wipers here. There's a wiper for the say, let's call this the A. Let's call that the A. Call this the B. And this is the common. Okay. So this is the common terminal. This is the B terminal for the encoder, and this is the signal for the encoder. So what it does, so these slide onto like a disk, which have like contacts in the disk, well, little pads. And as this rotates over these switches, let's just select all that and go like that. Oh, let's get rid of that as well. So make it a bit bigger. There we go. Well, something like that. So what happens is when we rotate the knob, we actually rotate this disc round like this. So we can rotate in that direction or in that direction, whichever. So what happens is when the wiper gets over a let's go that way. Yeah. So you can see that this wiper here now is making contact, is joining these two pads together, and this one isn't. This one's still open. So if we look across to this table here, we can see that. Well, actually, imagine that. Can I draw another line? I should have put that inside a thing, but if you imagine this line is not here, it's over here. It's actually touching this one but not this one, and so we've got this one turned off, and as we move along this dotted line, as this dotted line moves along the this drawing whatever sketch, it represents this turning. So if this turns a little bit more, what if we do is we get to that position there, you can see that this one is actually on closed now, and this also is closed. So we come to this position where this actual line is, and you can see that we've got a spike there, so we've closed them both. But then as we turn, so as this moves in this direction, as we turn, I've got the clockwise and anti-clockwise the wrong way around, but it doesn't matter. As we turn, what's going to happen is that this is going to open here, so you can see that this contact has broken now, but this one is still closed. So you can see if we would move to this point here, this one would now be open and this would be now closed. And then we'll get to a point where they're both open, so we'll keep rotating, and we rotate to say about that position. You can see that they're both now open, and there's no contact, so that is at this position here, and then it repeats. And if we go in the other direction, basically the sequence of events where it goes both open, one B open and A closed, and then we've got both closed, and then we've got B closed but A open. You have a sequence. Basically what we can do is, I can just maybe just write that in there. Oh, I don't like that. Right. What we could have is we could have both open, then we'd have one closed and one open, then we'd have two closed, and then we'd have one open and one closed, and then it would repeat again. but you can see that there's a sequence where we either have A before we get both closed or both open. Well, I'll tell you what, let's just repeat that and then you can see it better. Both open, and then we'll go one open and then go both closed. So this is the sequence going in one direction, so you can see that before both are actually closed we've got it. Let's just put an A and B there as well. Let's put A, B. Okay. So you can see before the both A and B are actually closed, if we're moving in this direction, then we've got an A closed and B open before that they're both closed. So we can determine, if we watch this sequence of events, we can determine that if it's going down in this direction, we're going clockwise. But if we were going anti-clockwise, we would have A open and B closed before we get both closed. Can you see that? This is different to this one. So if this was the state before this state, then we know that we're going anti-clockwise. And then if this state was before this state, then we would be going clockwise. This is how we determine whether we're going clockwise or anti-clockwise, and so we can determine we're counting up or we're counting down. I hope that was clear. I hope this sort of this is the sort of signal as we go, so going clockwise. Before this state where both are closed at this point here, if we're going in this direction, this one was actually open, but if we was going in this other direction, this one was actually open. So we've got this, the opposite pins are actually open and closed, determined before both are closed. I don't know, I'm not good at this. Anyways, so I hope that made that clear, how this actually, an encoder actually works. As it turns round, it's connecting one terminal, then it's opening both, and then it's connecting another terminal, and then it's closing both, and so on. And it works. Let me just move this again for you so you can sort of see how it works. You get one before the other one, and then the both, and then one opens before the other one, and then the both open, and so on. That's best I could describe it, really. So just give me a minute and I'll set up the code. Okay, let's continue. Right, for this demonstration I'm actually using a cheap old nano tiny board, and I think I've mentioned that it doesn't have UART on it. We can look at that. This is the data sheet for the tiny 88. Well, if we look at this, you can see the 48 has 4K 8-bit, and the 88 has 8K 8-bit. So if we look at the peripheral features here, it's always good to look at the data sheet. We can see it's 8-bit and there's a 16-bit timer on there, but later on with Project X I will be needing the analog to digital converter, so that's a good thing. That's on this chip, and it's also got I2C. Well, we don't really need that, but as the SPI, that's what we're programming in it with, and that's about it really. But what we've got is if we looked at the ports, let's have a look. Yeah, we look at the parts, we can see that there's 1, 2, 3 ports on this one. It has this extra port A that the normal Arduino Nano doesn't have. But anyways, I just wanted to just point that out. So we don't really. We can either use the data sheet and get the pin details here. So if we zoom in there, whoa, there we go. Zoom in there. This is the chip that's on the board, so we can find all our thing there, pin details. But because it's on a module, on a nano module, we may as well use the one. It's easier to use a different picture like this one. So this is what my little module works with the tiny on, and this actually lists the. If you're using right, so I'm using Arduino Nano code, but also not when it comes to the pin numbers, right? So this I'm going to compile this using the Arduino IDE. So some of it is in Arduino and some of it is in AVR. And I just wanted to point this out because normally with an Arduino Nano you have two pins with interrupts on. These are special pins and there are special interrupts, but we can't really use those interrupts on the that tiny, or it may be some other different microcontroller we're using. And so my interrupts for the interrupts, I tend to use the global interrupts, and which basically let's see, a microcontroller usually has loads of pins, and it's usually 8 pins. 8 pins are to a specific port, so you have a number of ports and they will normally have 8 pins, whereas this tiny has 3 ports, and it on the A port it has this port A, it only has 4 pins, whereas if we look at the PC5 port C, you can see 1, 2, 3, 4, 5, 6, 7, and well, oh, sorry, no, yeah, 1, 2, 3, 4, 5, 6. Hang on, where's 6? Oh, well, it isn't there. Let's have a look at the other one. There. Port D has got 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So it looks like reset is on port C there. So we can't actually use that. But it's a pin, has to be attached to a port. Anyways, I'm rambling. I'm rambling. Right, yes. So in my notes, I've put the I do my interrupts to the actual AVR architecture and not the Arduino architecture. So this will not run. This code. What I'm saying is this code will not run on a normal Nano. This code is written specifically for the T88. And so I will show you what needs changing if we need to put it onto a Nano. So let's just go down. This is just my debugging. Like I said, the T88 doesn't have UART, so we can't have the serial print because there's no chip on. Well, because it doesn't have a UART, we can't put a UART to USB chip on there, so it doesn't have one. So we need other ways of doing diagnostics. So I do a visual diagnostics by I write code to either light up the blue pin or the green pin or the red pin, and that gives me some feedback to when you're coding. So you don't always, if you can't use serial print, then it's usually use some pins to light up an LED to give you an indication of something is happening when it should be happening. We need some timing because we want to be able to turn on the LED's display, our LED's display at certain times. So that's my timing. So now I think I did all that before, didn't I? So I'll just stick with the quadratic encoder. Now what I use is a structure. I have a standard. I have a piece of code that I use all the time, and if I come up with a better idea, I will edit it. But as it stands, I have a structure which has a boon for a bullet, a boon for a button. So the button is either pressed or it isn't, and it's either being rotated in the positive direction or it's being rotated in the negative direction. So that's either true or false there, so I can set them as being true or false. And then if some user interacts with the encoder, then I need to set a flag to say that the button on the encoder has been pressed, or the encoder has been rotated. And then, as I was discussing before, let me just bring that up again. Not that one. That one. As I was discussing before here, we have a sequence of events that happens as it rotates. Where's the other picture? That picture. So I'll get rid of that one. Right. So as we have a sequence of events that goes on and off, to compare whether it was O1 prior to both being on, or whether it was 1O prior to being on, both being on, we need to know the last state of the two switches. So this is what these two do. These hold the state of the two switches, the previous state, shall I say, and then what we do is we get the current state, and then we either alter the actual value. I have two values. I have value A for when the button is up, and I have a value B for when the button is down. This seems to work for most scenarios that I use with the quadratic encoder, so let's continue. Oh yes, first we build the quadratic encoder and we give it the sort of default values. We give that's the pin number for the button, and this is the encoder pins for the encoders. Now it's a good thing to, where's that other picture? Right. So what I could have done is put all pins. I could have put it on these three pins here, 15, 16, 17, but these are all on one port, and it's a good thing to separate the button and the encoder onto separate ports. So when you interrupt a sequence, then you can have two different routines for whether it's a button press or whether it's an encoder switch movement. So what I have done is I have put the button on port C, and I've put the encoder on port A. We'll see that later on. So yeah, so that was similar to what we've done here before for the segments. I just put it in an array. Makes it easy. And then we define them as normal. So what we need to do is we need to define the interrupts. Now this is where it is not Arduino. This is the AVR part for the architecture of the actual manufactured chip, shall I say. And so what we need to do is we need to tell it which pins we want interrupts on, and what we want it to do when that pin is interrupted. So basically, if you look into a datasheet, you'll find that there are masks for each port, and each port has an interrupt number, and that interrupt number corresponds to an actual pin. So we know what pins we're going on, which is, well, that's the Arduino numbers. This D15, 16, 17, that's Arduino. What we want to know is the actual pin that these Arduino numbers go on the actual microcontroller. and we can see that by looking at that this is on port A pin 3, and this is on port A pin 2, and where I'm putting one on here on port C pin 0. So yeah, so what I did was I put my meter on these pins and found what actual pins there were on here. So what we can see here is that if we look over here, we go port A pin 2 is actually on pin 3, and port A3 pin 3 is actually on the physical pin 6. So that's what I have written here basically, so I know what I'm going to. This is notes for when we this is notes for when we're not doing Arduino pin numbers, but because I'm getting this compiled by Arduino, we can actually use the Arduino pin numbers, which I've used here. There, so we've got 19, D19, which is PCO, and 15 and 16, which is these two. Because it's been compiled by the Arduino IDE, I can use these numbers as the pin numbers. Arduino IDE actually converts these numbers into these numbers, so I don't have to worry about that at the moment. What all I need to do is worry about is the interrupt numbers. So I can see that these two pins refer to 26 and 27. So on mask 3 I need these two values set. So if we look at the mask 3, I've actually set them two values to accept interrupts. And on what's it, PCO, yeah, I've written notes here, PCIO, which is pin 23, Arduino, I've put Arduino stuff in brackets. Pin 23, which is here, I can see is on, that is on mask 1, and it wants to be this first one. So on mask 1 I need to tell it that I want this to accept interrupts, and then this one here turns on the global interrupts. Now when an interrupt happens, this is for this is an interrupt sequence request. So if there's an interrupt sequence, this requests for my port 3, this one. So if any of these two are interrupted, you know, when we turn the knob, oh sorry, we're looking at this one, aren't we? So this one, this PCI int 1 vector, so this one. So when the button is pressed, what it'll do is I will turn this flag on. This is my rotary encoder. I want to do an external interrupt on port C to true. So you can see here that I've got my port C, which is 1, 2, 3, 4, 5. Which you see in my encoder 1, 2, 3, 4. It will set this value to true here. So yes, so this is just simple because this is just for the button press, and if it goes through the loop, if we look at our loop, and what we'll do is we'll check for this flag, and let's highlight it there. So it's gonna, if I've set that flag to true, when we go to our loop, it'll look to see if the rotary encoder flag is true, and then what it'll do, it'll turn that flag off because we've spotted it and noticed it. So now we want it to turn off, otherwise it'll keep doing this, and then we'll do a pin change. So what we'll do is we'll pin change on C, on port C, which is down here, and all this is just, this is my button which I showed you, and it just, if the pin is on, if the pin is low, it'll turn the LED pin on, and if the pin is high, it will turn the pin off, because the interrupts whether the pin goes from low to high or from high to low, so we need to put the both scenarios in there basically. So if we go back to the other one, which is this one here, this is for the two this mask 3 is for the two pins that are A and B of our encoder. This goes down here, so it will call this interrupt sequence routine. So this is this. Now when you do an interrupt, you want as little as possible in there, so you don't want it to actually sort of change pin values or light up the LEDs on the 7-segment display or anything. You don't want to do that. All that wants to be left into the main loop to do that activity. So what we've done again is we've set this do extension A, this external interrupt A, to true again. So if I highlight that one, we can see in our loop we've got a similar thing to our C, which if that is true, then we then change it to false to turn it off, because we've caught it already, and then we do pin change A. And what pin change A does is all it does is actually just checks to see if the value is higher than a value manual, but the work is done here. But what we've actually done in the interrupt is actually set the value. We can set flags and values. That's all you really want to do in an interrupt, because an interrupt, we want the interrupt to do, if it's changing a value, like it's making value B bigger, or it's making value A bigger, or value B smaller, or value A smaller, we want it to do that immediately when it's interrupted, because you may interrupt when you're flicking that switch around really fast. It might put maybe 3 or 4 interrupts in there before we actually get through the loop. So you need to be changing the actual values here. I'm sorry that this is going on a bit long, but I don't know a quicker way to explain it. So anyway, so that's where this is just explaining how I do interrupts, because we actually need 3 interrupts, and the normal Arduino IDE only architecture only has 2 interrupts, and those interrupts are special interrupts, whereas I've put in global interrupts, and I need 3 of them. And I just wanted to share, so tell you that you need to stick them on separate ports, so that depending on which port is activated, it does independent routines. I want both these pins on this port, because this routine actually compares the two. What it does, it reads the 2 pin states, it compares it to the, you can see that's that sequence A there that I talked about. It compares that sequence with the current state, and then depending on the current state and the previous state, it then either increases the value or lowers the value on this. This is the lower, if these match. And then the loop will then just update as before the encoder with the new encoder A value that we've actually set in this interrupt. So the interrupt keeps this value, keeps track of this value, but we're still just displaying the LED. I hope that made some sense. And I hope it gave you a bit more insight into actually coding encoders. I'll end it there. Yeah, I think it's enough.